final speaker for today, Loren Sands-Ramshaw. Loren maintains Temporal's TypeScript SDK. They also wrote a book on GraphQL, the GraphQL Guide, and spent over a decade doing full-stack web and mobile development. The title of his talk is Building Reliable Distributed Systems. Please give a warm welcome to our final speaker today, Loren Sands-Ramshaw.
Hi, everybody. My name is Loren. I am happy to be here. I'm happy I eventually found the green tent. I was wandering around asking people, where's the green stage? And is it in the green tent? Where is the green tent? And eventually I found it. I'm glad you all found it too. I hope that, feel free to stand up and leave at any time. I won't be offended. But if you are leaving because I've lost you and you're like, what's going on? I invite you to instead ask a question. Just shout out question. We will get you a mic. So feel free to interrupt me. If you have the question, someone else probably does too, so you're helping someone else, and you're also helping me figure out how I can improve this talk in the future for other people. So building reliable distributed systems. My name is Loren. As I already said, I wrote a book, and I've been doing full stack development for a long time. My first job was in 2007, working with GWT, Google Web Toolkit, which was a cutting-edge framework that compiled Java to JavaScript for websites. And I've done a lot since then, and I'm currently a language runtime engineer at Temporal, working on their TypeScript SDK. And we'll get into what Temporal is later. I'll start out with what's a distributed system, how to make distributed systems reliable, and why you can use Temporal to make that easier, and then how to use it. What's a distributed system? Wikipedia says it's a system whose components are located on different networked computers, which communicate and coordinate their actions by passing messages to one another from any system. So that's pretty broad. If I take out my phone and I have a single server on EC2 that has an HTML page that just says hello, and I take out my phone and I go to that website, that's a distributed system because there's two network computers. They're both on the internet, my phone and the EC2 instance, and they're communicating. So that's technically a distributed system. It's not often what we think of. Usually we think of multiple back-end services or systems that are communicating with each other. And so going from a simple monolith to microservices, there's lots of distributed system concerns that come up. When we're just talking about the monolith, say we have a single monolithic app server layer and a single database cluster that supports transactions, then what are our concerns? We have a client talking to the server. If the client can't get access to the internet, then they'll just retry. If our server is temporarily down, they'll get unavailable and they'll retry again. If they get to our web server and we get the request and we're up, then we do a single transaction with the database. If it fails, we say, hey, sorry, client, it didn't work out, and the client will retry. If it succeeds, then we respond success. So not a whole lot of failure modes, and what we do is straightforward. We send the client basically winds up retrying in all the different cases. When we have multiple systems sort of in the business process of processing our client's transaction, we have more things that can go wrong. So let's say that we're still on a monolith, but we need to first talk to Stripe to charge a user's payment method, and then we need to update our database. So there's two different steps once I get a request. Let's say I try to talk to Stripe and I can't, then I'll return failure. But let's say I successfully talk to Stripe, and then they think that we charge the card, but then before I get to the next step, there's a failure, like my process dies or my database is temporarily unavailable. So I wind up, unless I handle these failures, I wind up in a place where Stripe's view of the world and my database's view of the world are different. or inconsistent. And yeah. So that's just like a simple case with two things, but when we have more things, more places we need to talk to, whether they're internal or external services or data stores, then we have more potential failure modes and more potential data inconsistencies. So in this example, we will write an endpoint for a post, creating an order, and then we will try to make it reliable. And we won't get to complete reliability because that would take a lot more code and time. But we'll see how much code is added in each step and how much it would take to get to full reliability. And then we'll simplify it using the Temporal SDK. And Temporal is a open source framework for writing reliable code. So starting out, we have a serverless function hosted on Vercel. We get a single request, and so whenever someone hits the post to the order endpoint, this function will respond, and inside the request we'll get from the body the item that the user wants, the quantity, and the ID of the address to go to. And by the end, we're getting that out of the request, and by the end we want to send a response. We're also getting from the auth header token the user ID. And we have sort of 3 steps to do in this imaginary backend system. First, we talk to the inventory service, and we reserve a quantity number of that item. And then we charge the user for it. And then we fulfill. We send the package to the user. And in this is like a really simple function. And in the case where so this is a TypeScript. Yeah, if anyone ever has questions on TypeScript specifically, feel free to shout out. So in the successful case, this works. The logic is fine, and we will send 200 status HTTP response with this text. So what are some problems? One problem is that any of these 3 steps might fail, whether it's because I can't reach the service because of the network outage, or the service is down, or the service tries to process it but comes into some error and returns an error to me. In any of those situations, I will want to either retry or compensate for the things that I've already done. So this is called a saga. If you were in the talk, when was the talk? This one by Ford. You heard a lot about the complexities of this. Whoops. Where? There we are. So if we successfully reserve, but then when we try to charge, it fails, we want to go back to the inventory service and unreserve it. If the first 2 steps succeed, so we've charged the card, but then we are unable to fulfill, like we get some error from the fulfillment service, then we want to refund the payment method and then also unreserve the inventory. So let's see what that might look like. So here's the same function, but a new version with some added logic. If the reservation fails, then we send status 400. Sorry, we don't have enough inventory. If we successfully reserve and then charge fails, then we want to tell the inventory service to unreserve it. If we successfully did reserving and charging, and when we're sending a package, if that fails, then we want to refund the user unreserved. Each of these is, say, like doing a single gRPC thrift or REST request to the service. And any of those could fail. Ideally, what we'd like to do is not just try it once, and if it fails, then report failure and compensation logic. We want to retry, and when we're retrying, we also want to have timeouts. So like, I send the request, and it's been 30 seconds. I'm going to give up and retry again. So let's add that logic. And now we're looking at a diff of what's been added, since it's getting a little bit more complex. So we have a retry function that we're going to reuse. And we have the service call that we want to make, that function. Maximum attempts, how many times we want to retry. The timeout for each request, how long I want, how the maximum amount of time I'm willing to wait. And then the interval between retries, and we'll have exponential backoff. So this is just the first interval. So we've got a loop until max attempts, which is 10. We race here between the service call and the timeout. So whichever one of these resolves first, either the service call returns a response or the timer fires, we will finish based on whichever is first. And if it timed out, we'll throw an error, which will get caught, and then we'll set a new timeout for interval with exponential backoff. And then if we ever reach max attempts and we don't have a result, we'll throw it. Otherwise, we'll return. So that's the retry function, and we're going to call it and pass the function that calls each of the services. There's reserve and charge and send package. So one issue that comes up when we start retrying things is idempotency. So it's possible that, say, on this step, we successfully reserved and retried the first, now we're charging. The first charge technically succeeds, like the service thinks the service does the charge, or Stripe does the charge, but it, I don't like this function, I is the execution of this function, don't receive the response. So I retry it, but the next time it's like a double charge. So I want to prevent that by providing an idempotency token to the payment service. And usually the nicest way to do this is for the client to provide a request ID to the server. So like if the client has a web form and someone like double clicks the submit button, the client will make sure to use the same request ID. And then I, as the API function, will always be sending that request ID to each service and depend on them to, if they have already done a payment with this particular request ID token, and they receive another one, they will drop it and say, error, we've already done this. Or 200, we already did this, I don't know. So that's the idea of the request ID. And so here is adding it. We're just getting it out of the request body and then passing it to each service. What next? We also, so we retried the happy path. We haven't started retrying the compensation saga logic. So let's add retries for each of those. All right, here we're wrapping each of these in a retry. We aren't catching errors. So we'll notice that the retry function, if there's, on the 10th attempt, we get an error, then we're saving that in this error and we're throwing it. But it's not being caught right now. So let's say inside this charge retry, that's going to throw. We're not catching it currently. We want to like dot catch or try catch either way, and then do the compensation. So here we are adding catches, saving the error, and if there's an error, we send the response 400 with the error message. And we'll do that for each of the 3 service calls. Another thing we need to do is consider what happens when this process fails. Say the machine it's running on loses power. We want to be able to know which step we were on so that we can pick it back up. So for instance, if we, let's say, we just failed fulfillment and the process died like before executing this line, then we want to be able to know where this process was, and so that we can pick up and do these 2 calls. So let's do that. So we need like a set of different states that we're in, and we need to save it to some durable store somewhere. So we have a MongoDB client and different states that the order can be in. First we create, then we reserve, then we pay, and then we fulfill. So the terminal states, the states that this should end in are we failed to reserve, or we failed to charge and then we unreserved, or we fulfilled successfully, or this one. So those are the terminal states. And here we're connecting to the Mongo database, the orders collection, and this is the first thing we're doing inside of the serverless function. I guess the first thing we're doing is inserting one order created record into the database in the created state. And so if that fails, then we send an error to the client. And then we're saving the ID of this a document that we just inserted, so that we can use this ID to update that order document after each step. So here, the reservation failed, so we say failed to reserve, and then if it succeeded, then we say it's reserved. And if the charge failed, then we say we update the state again. Similarly, we also keep track of which stage of compensation logic we've done. Are there any questions so far? Let's get you the microphone just a sec.
I can talk really loud. Okay. So this looks like a bit of a never-ending story, because now the database writes can fail.
Yeah.
And so on and so forth. So is there any end to this? It just gets more and more complicated.
There is an end, and I'll talk about
Okay.
where we would get to, if we kept going. So each of these database calls could fail. So we want to make sure that whatever database client we're using retries, and we want to handle the errors. Right now we're not. And we also need some other processes, like a worker pool, to pick up the fact that one of our orders is not in a terminal state. So let's say in each of these updates, we also have like an updated at field, something like that. We need something that's like checking the database periodically, like polling, to see, okay, are there any orders that are in a non-terminal state that their last updated at was like over an hour ago? And say, I know that if there is a process that's currently working on an order, it should be getting to the last state within an hour, or it should at least get to a next state within an hour. So all of the old things that are not terminal, I need to check them, claim them, like atomically, and then continue processing them. And by continue processing, I mean like jump to this place in this function that the state is at. So like currently, so say my worker pool polled and found one in this state, fulfill refunded, it would need to go to this line of the program and start executing. So this code needs to like be re-architected into like a state machine where I can jump into any piece of the logic. And like, especially with these retries, the execution time of this function is going to get beyond the maximum execution time of a serverless function. So I can't be putting it this here, and also ideally I would be replying to the user sooner than the end. Say maybe right after I created this order or right after I checked inventory, then I respond 200 to the user, and then later try doing the charging, the fulfilling, and then sort of like out of band asynchronously notifying the user if there's a problem with payment or fulfillment. So those are some added things that need to happen to get to more reliability. And I don't go any farther with that, but we can see how easier it is with Temporal. Oh, so this is the full function that we just built with the retry, the order states, and the function. Scroll, 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 scroll. scroll. OK. Now this is the temporal version. We are creating what's called a workflow client, which comes from the SDK that I work on. And we just do a single thing. We are starting a process order function with these arguments. And we're using the request ID as the idempotency token. And task queue we'll get to later, but this is there's a worker pool that's asking for new tasks on this queue to continue processing each step of this order. And once this successfully started, we know that there isn't an existing workflow or process order function running with this request ID. Otherwise, we would have gotten this error. And we say it's submitted. So this, what this says is, if this returns successfully, we know that the function has been received durably by the server and will eventually go to completion, however we define that in the function. So it's safe to return 200 because I know that it's been durably saved. So let's look at what this function looks like. Here's the process order function, and it's kind of simple. We reserve, and then we try charging. If the charge fails, then we unreserve. Then we try sending the package. If that fails, we catch the error, refund, and then throw, which gets caught here, which unreserves. And that's the whole thing. You might be thinking, OK, but each of these functions must be really complicated. It must have all of that retry logic that we had over here, or over here. But they don't. They're actually pretty simple. So they're coming up from here. Let's look at what reserve looks like. It's just a really small thing, just calling the same service function that we were doing before, getting the request ID sort of from the execution context. This is the workflow ID that we set back when we started it out over here. So those are called activity functions, and this is called a workflow. And it's really that simple. And each of these activities are automatically retried and timed out. Here's the one timeout that we have configured currently, but there's lots more that we'll show later. Yeah. And this is much simpler to write. And I guess we'll get to now sort of how this works and what the other things we can do and other parameters that we can provide, and see some more code later. That's not it. Here we are. So Temporal is the open source runtime for managing distributed application state at scale. So open source runtime, we're MIT licensed. Anyone can use it. Distributed application state at scale. So the state of like where we are in that business logic of reserve inventory, charge, user, fulfill. We automatically save where you're at in this function, such that durably. So like if the process dies after this, we know to come back and try this. And similarly, we're taking care of all of the retries and timeouts for each of these functions, the activity functions. Why? So the most valuable mission-critical workloads in any software company are long-running and tie together multiple services. We're used by Uber for a ton of use cases, including like the main flow of starting a ride and the entire flow of the ride of like matching the driver and like payment and rating them at the end. Used by Netflix, Coinbase, Stripe. So sort of the system requirements that this type of system in general fulfills are, because the work is complex, we want to easily model dynamic async logic and reuse, test, version, and migrate it. So we want workflows as code, and we'll see workflows as like config files later, which we can't well reuse, test, version, and migrate. Because this business work that we're doing relies on unreliable systems, we want to standardize timeouts and retries so that we're not coding it in every application, in every function. We want to offer reliability on Rails to every team in the company, so that they don't have to do it over. They don't have to code the same thing, and also so that it's coded well, because it's hard to code it completely reliably and scalably. Because the work is so important, we must never drop it. You have to log all progress, and you have to be able to scale it up without replatforming. So we need orchestration when we have unreliable systems, and we need event sourcing is the never dropping any work and logging all process. So the status quo is either sort of ad hoc or choreography, and the most direct way to solve any problem like what we coded is to use like a duct tape of durable timers and queues. So you need the queues for the worker pool tasks, and you need durable timers for like timeouts and how long to wait until the next retry. And that is gets brittle and hard to maintain and hard to understand. And when things go wrong, it takes a while to figure out what did go wrong because it's so complex. So it's just hard to get right, hard to maintain consistency in the presence of failure. Yeah, hard to maintain. So on the right hand, we have orchestration. And there's sort of two columns. There's app devs on the left and the cloud cluster platform on the right. So on the left, we have your app. It could be a serverless function like we saw before. It could be just like your API server. It could be a script that uses the client to start a workflow or to start one of these business functions. So the client sends commands to the cluster, the cloud platform on the right, which inside of it has timers, database, the gRPC gateway that receives requests, state machine, queues, and transactions between all of that, or transfer queues when it's not possible to scalably have a transaction across it all. So either consistent transactions or eventual consistency with transfer queues. And then on the left side, we also code the workers, and the workers are the combination of the process order function that we saw and the activities. So this is the naive way to coordinate multiple services. Service A just synchronously calls service B, which calls service C. And then you realize, OK, each of these requests might fail, so you need to add the retries and timeouts at each system boundary layer. And this can get complicated as we have more microservices. Netflix and Twitter have over 500. And here's, for instance, AWS's recommended way to do retries between two services. And it involves 3 queues, a Lambda function, and an in-person operator. And this is a system diagram of a more complex architecture. So what generally people find is that regardless of whether you're directly calling or using choreography, it gets much simpler if you have a single place orchestrating the sequence of calling and error handling of the different services, and that's called microservice orchestration. And in Ford's talk, he goes through some of the trade-offs between each, and in particular types of each, and the author of Richardson, the author of microservice patterns and microservices.io, recommends using orchestration over choreography for everything but the most simplest of use cases. I would argue that it's still hard to get even the simplest use case correct, so you might as well, and you're probably going to have more complicated use cases later on, so you might as well start with orchestration. I guess a little bit on choreography, if you're not familiar. Usually you have one service publish a message on a message bus, like a Kafka topic, and then you have consumers of that event stream that decide, like the next service B, will pick up that event and then do the next step, and then either publish like a success message on another topic or an error message. And if it's an error message, then the first service will know to undo it because they're listening on that error topic. Or if it's a success, then the next service, system C in this case, would pick that up. And the challenge with doing that right is some of which Ford talked about. So I recommend you check out the video if you didn't catch the session. Are the difficulty in making sure that each boundary there of like publishing and receiving a message is done consistently, reliably. So, for instance, system A, before it publishes the "I did this" message, you sort of have to both send the message and update your database in a transaction, and you can't really do that because the Kafka message queue is not what the service is using for maintaining their business state. So what you have to do is like every time you're publishing things, you have to use what's called a transfer queue to make sure that eventually you will always send that message after updating your own service's data store. And then on the other end, system B listening to that topic and getting that event. They have to make sure that once they get the event, they always update their store. And if they don't, they have to make sure that another consumer will handle that event. So lots to do on each boundary there too, which is why I think orchestration is just much better. Here's a great article on the difference. On the left, we have choreography, where each of these Lambda functions or services are talking to this event bridge in the middle. And different of the functions are like getting notified and responding to events that go into the event bridge. And it's on the right, we see the orchestration example where we have a DAG, a directed acyclic graph of what happens at each step. We start, then we notify the restaurant, we wait for accept, and then we can see sort of decision trees. So it's much easier to sort of model and understand the right side than it is to understand what's happening on the left side. And complexity leads to time and bugs. So you want to be able to understand the system you're working in. So work in the right side. So this is the typical programming model for orchestration is not really programming. It's editing either like a drag and drop DAG graph or editing config files like JSON, XML, YAML. And you're saying like, okay, this is the first task, and then here's the next task. But if you get a failure from this, then go here, and you're trying to like write that in JSON, and it's hard to read and write. And I guess when programming, it's easiest to program using a programming language. So that's our philosophy. So we don't use this typical way of orchestration. We use workflows. So typically, we call a set of orchestrated operations a workflow. So we write our workflows in Temporal with code. So on the left, we have the JSON version of a workflow, where we have a HTTP GET, and then we have a switch statement that goes to one of the other steps, sort of like a go-to statement in Fortran. And on the right, we have what the equivalent is in TypeScript. And it's much easier to read. We do this GET request. Depending on the result, we do one other. And the thing on the right, we can reuse. We can make reusable functions out of it. We can run the type checker compiler on it to see if it compiles, and we can lint it, and we can log debug it. We can breakpoint debug it. It's just a better experience, more effective way of developing. Here's a simple workflow function. The parts are like the signature, which is the name and the arguments, and then the implementation. And here's an activity where we fetch from the Stripe API, and we basically just call it from our workflow. And the difference between workflows and activities, so we have to set up some constraints in order to provide the guarantees that we need to. And what we do is workflows have to be deterministic. We have to be able to, the system has to be able to replay them and always get the same result given the same input data. So we can't, inside the workflow function, we can't get the current time or math.random or make network requests directly because we might get different responses at different times, which is not deterministic. So what we do in the TypeScript SDK is we run workflows functions in v8 isolates with set values returned from math.random and date.now, et cetera. And also prevent you from using system APIs like file system or HTTP network stacks, et cetera. So inside these, preventing you from doing non-deterministic things, but we allow you to call activities which run in the normal node context and can do whatever they want. So for instance, this activity is importing the fetch module to do a request to Stripe. And that's sort of the activities are retried and timed out. And that's sort of the programming model that we need to put in place in order to have these workflows guaranteed to progress in the presence of the process failing or anything else going wrong. So here are the different timeouts and retries I talked about before. Start to close, schedule to close. So let's look at these concepts. An activity is scheduled when the workflow hits this line of code, the charge line, and returns to the cluster saying, start this activity. So that's or schedule this activity. And then when it started is when a worker picks up an instance of that start activity command and executes this charge function. It might fail, in which case the cluster will put a new start activity command on the queue. So start to close is from the start of the execution of the charge function to the end, and then the schedule to close is from when this line is first hit, the charge line, to the end of all of the retries of the single charge function. So that's the difference between schedule to close and start to close. If you have long running activities, they can heartbeat, and then you have the maximum heartbeat time is the time after which you should consider the activity function as failed and schedule another retry. Yeah, those are the main ones. So here, start to close. So each charge function shouldn't take more than 30 seconds. Schedule to close. If you retry these max 30-second functions enough times, and 5 minutes have passed, I want you to give up and return an error. And then retry logic is configurable. If we didn't have schedule to close, it would never close. It would retry indefinitely. or forever, because the default retry policy is maximum times infinity. So initial interval, 1 second. Backoff coefficient 2 means the exponential backoff will multiply by 2, so 1, 2, 4, 8. And then maximum interval is like not the point at which we stop retrying, because we're maximum times is infinity, so we're always retrying. Maximum interval is like, OK, once the interval between retries gets to 100 times 1, so 100 seconds, just keep it 100 seconds forever, or until maximum intents. So we sort of touched this a little bit before, but the temporal sort of system has 3 different parts. There's the client that we use to start the workflow. Then there's the cluster. So the client talks to the cluster. The cluster has a number of horizontally scalable services inside of it, and a Cassandra cluster. And then there's a worker fleet. And then the worker fleet has the code for the workflows and the activities. And it pulls the cluster for any new tasks on the certain queue. So 3 parts. The client can be used anywhere. It could be in a serverless function. Could be in a script. Could be an app. It says, hey, cluster, I want you to start this workflow. The cluster says, OK, I've stored it in the database, and it has a unique workflow ID. You can consider it started. And I promise that we will finish execution at some point, once all of the retries are done. And then there's the worker fleet, which is polling the cluster, asking for new tasks, like start this process order workflow, or start this, try doing this charge activity once. OK, now try doing it again, because it failed last time. So the worker fleet are long-running processes. And in both the client and the worker, on the left side, application developers, is depending on which SDK or language runtime you're using. I maintain the TypeScript one, so it's Node, but there's also PHP, Java, Go, and we're working on .NET, Python, Ruby, and Rust. So let's look at the code and connect it to. So here's a samples repo for the TypeScript SDK, and we've got a lot of different samples. And I'll open this up in my editor, and then we can see sort of what's happening in this 3-part system diagram as we're doing the code. No, that's not it. There we go. OK, so this is the GitHub repo we just looked at. And whoops. I guess, actually, let's do a break for questions before we get into the code. Any questions about how it works or why it works that way?
So I just want to get back to my previous question, that basically what I see here is that on one hand, you expose a library that makes it easier to write the same code that you showed us at the beginning, and you also supply some sort of cloud infrastructure that takes care of the persistence that you showed us with MongoDB and in the first example, right? Now, what I don't understand from this is how does this temporal cluster guarantee that, like the MongoDB in the first example, doesn't simply crash or disappear in some place of the web? Because my original question was about if you keep adding new things to log your progress in a service, as we did with the MongoDB example, we are just introducing new services to our flow that usually work, but can likewise go south in some cases. How does this infrastructure take care of this problem?
Right. So I guess stepping back, if you want to do reliability, there needs to be that complexity, and there needs to be at least one database. and the complexity needs to live somewhere. And Temporal allows you to have it live in the cluster, versus if you're not using that, then you are sort of setting up the queues and timers and data stores and logic yourself, and dealing with the complexity yourself. In terms of how the cluster provides the guarantees, I can skip ahead to so here's sort of design of an orchestration system or a workflow engine in stages. So the engine needs to get commands, like what step do I do next, and execute tasks. And so it can't do this sort of synchronously like this graph implies. So we need a task queue with workers pulling the queue. So get commands, add to the queue, do this task, and then worker pool picks up the task and says completed, etc. And we need to add timers. So once we add a workflow task, let's see, then the queue picks it up, say, okay, I need to check what the next step is, and then, okay, I need to do task 1 or an activity 1. So we add it to the queue, and we add a timeout to the queue, and then the worker pool is picking up the tasks, or we're getting a timeout if it doesn't. And we need to have transactions between both the engine state and the task queues and the timers. So if you use the same data store for all three of those things, the workflow state, the timers, and the task queues, then you can have transactions. And we support, our cloud offering uses Cassandra, and that's the recommended one, but we also support Postgres and MySQL. And I guess in order to do this scalably, we across different app layer shards and Cassandra shards, we can't do this all in a transaction because the task queues, for performance and scalability reasons, need to be in different shards. So what we do is the engine state and timers are in their own shard, and then we use a transfer queue to eventually get that state into the task queues. Yeah. And then, so it's a little complex. There's a YouTube video I recommend from our CEO on our YouTube channel on designing a system and how you get to this place. And then in terms of like how, I guess, how the code translates to commands that get to this cluster. I guess we'll see a little bit on how that's done in the code sample. Were there any other questions? Awesome. So Hello World is the simplest sample. We've got a few source files. We have the client, and then a worker, and the worker has workflows and activities. Actually, let's make all of these in separate tabs. Okay, we start with the client, and then we have a worker running that has both workflows and activities. Okay. So what does the client do? It creates a connection to the cluster and calls start. I want to start the example workflow with these arguments on this task queue and this workflow ID. And so we can run this client right now. So I have the cluster running locally. So this will npm run workflow will run this client script. And so it says start a workflow. And now it's, so this log line ran, and now we're waiting for the result. And there is no result because I have no workers that are listening on this task queue. So let's look at the worker, and then let's start the worker. and then the worker will pick up the task. So I'll show the cluster's view of the world right now. So one benefit to orchestration and this particular temporal is you get to see what's going on. So in the duct tape cues and timers, it's hard to reason about and see what's going on. But when you have a central orchestrator, you get great visibility and know how things are doing and when things go wrong, how they went wrong. So this is the workflow we just started. We can see that the workflow ID HZS corresponds with this, HZS. And the workflow type is an example, and we should probably be able to see the argument is temporal. Yep, input temporal. And we only have 2 events. So internally, we're using event sourcing to make sure that we do everything. We have execution started, and task scheduled. So execution started is what happened during this start, like before this returned. It's like always the first event. And then the cluster created a workflow task schedule, which a worker needs to pick up and run this. Where are we? Run this example function. So if we look at, we need a worker somewhere to run this function to see what it does. So here's the worker. It's a run script that creates the worker given this path to the workflow code over here, and given the imported activities from here. So the workflows are the deterministic business logic functions. The activities are the non-deterministic, could call an external API or do file system access, etc. And we're listening on the same task queue as the client started the workflow on. And we're just running. So we can run that. So this is running source worker, this script. And we can see on the left that after this became state running, after the worker finished starting up, it was able to get the start workflow command task and continue the processing of the workflow. And then this result came back to the client, and it printed this out. In terms of breaking that down, so here's what the last state was. I'm going to refresh the page. So workflow task started happened when the worker picked up that workflow task. It completed when the worker finished running this function, or got to here, basically. It said, OK, you're calling an activity. I'll return to the cluster that you want this activity scheduled. So the cluster schedules the activity. So we're getting this name, which was temporal, and we're giving it to this root function. So we can see the input to the activity here. And then the same worker, it kept on polling, and it got this scheduled task, and it started the activity. So what that was is starting this greet function, and then it got a return value, hello temporal, and returned it. Whoops. So we can see in the task completion that the result was hello temporal. And then the cluster adds to the task queue, start this workflow task again. So the worker picks that up and runs the example again, except instead of like pausing on greet, it knows what the response is now because it has the activity result from the cluster, and it does any steps after that, which in this case is just returning it. So then the worker will say, OK, I finished running the workflow function, and the result was hello temporal. So task started, task completed, and then execution completed because the workflow task function got to the end with this result. So those are all the steps. And so when this execution completed with a result, then our clients waiting on this handle.result, then that resolved to a value, and we logged it. And then this script ended. Yeah. So it's internally a lot of steps in order to get that to work reliably. But it's relatively simple code. We basically just had this start command and a short workflow function and a short activity. We can look at different. If there are any questions on how that works, I'd be happy to answer.
Just a quick one. So if you delegate all the calls to the cluster, that means that the cluster needs to have access to all your APIs, right?
That's a good question. So the API calls are happening in the activities, and they're not getting run by the cluster. The cluster is just adding a task to the queue saying, hey, worker, I need you to run this greet function and give me what the response is. And the worker pool is hosted separately. And like if you're using our cloud product, we only host the cluster for you. We're not hosting your worker pool. So that's controlled by you. And so we can't access the services or other internal endpoints that you're calling. Yeah. So the question is, does the worker pool need access to the APIs that need to be called? And yes.
Yes, and that goes to the other. The suggestion is to cluster worker pools. To cluster worker pools based on the access needed in the platform. Because if you have just one or two big worker pools, then you have a problem from a security point of view, maybe. Does this make sense? Because then if you have a worker pool which have access to all my APIs, then if I corrupt the worker pool, then we have a big problem, right? All the APIs are exposed.
Yeah, I'm not sure how often it's structured that way by companies, but certainly if you want that level of security, then you could have separate worker pools that have separate access and only are able to run certain activities or only work on certain queues.
Yeah, okay, makes sense. Just making sure. Okay, thank you.
Sure. Any more questions? Okay, so let's go through some of the, actually, let's rewind. So we did one of the code demos, and we could do some more later. So we have different workflow APIs. One of them was this proxy activity function is one of the API functions that come out of the workflow package. And this sort of allows you to pretend that you're directly calling this function when actually you're not. You're just returning to the cluster, schedule this activity to be executed. But you're able to like code it as if and get type safety as if you are calling this greet function directly. And you're also able to like set the timeouts and retry logic there. Another API is sleep. So because we already have built-in timers, you're welcome to access them directly. And so this workflow charges and then sleeps for 30 days and then charges again. So if you were doing this in a normal process, it's kind of risky, and so it would take up resources if you like have this thread blocked forever or for 30 days, and it's risky in that this process might die. It might you probably upgrade, push changes to your code, and that kills old processes and starts new ones. So it's unlikely this process will still be around in 30 days. So you wouldn't normally code this, but in our case, we could be keeping it around, but we're usually not keeping around this process for 30 days. What the sleep command actually does is it returns to the cluster saying, okay, set a timer for 30 days, and then in 30 days, assuming there's still a worker pool in existence in the world at some point after that, it'll pick up that task and then continue with the third line of code. So we can do this to implement a subscription workflow while true, so forever. We charge and then sleep until the next month. And this is perfectly good code that will reliably run. We can also, continuing with workflow APIs, we have signals and queries. So a signal is, hey, I've already started this workflow, and I need to give it more information or tell it to do something. So it's sort of like a method. So you can define a signal. This is update signal. And so up here, we're defining it, and then down here, we're setting the function handler. So whenever someone calls this update signal, so a client would be doing that, take the update amount and provide a new amount so that whenever we're charging, we're doing the most recent amount. So that's a signal. A query, it doesn't receive data, it just returns data, and it also doesn't mutate state. So if I wanted to query what's, for this particular user's subscription, what's the current amount they're paying, then I could define a query called getAmount, and then set a handler that just returned this amount value. So those are the two main ways of interacting with a workflow after it started. You can also cancel it, and you can have logic in the function that handles cancellation, or you can terminate, which is sort of like a sig kill. Here's an example subscription project requirements with a trial period and maximum billing periods, and the need to be able to update the amount charged or the number of periods remaining in the subscription. And here's that business need in code in 20 lines. We have, I think it's big enough to see. So it's a subscription workflow that has a cancel signal and sends a welcome email. And then unless either waits for the trial to be canceled or waits for the trial period to end, and then sends the cancellation email or starts this billing cycle function, helper, that goes in a for loop until the end of the billing periods. Yeah, and can also receive signals and queries, which are wrapped in this helper function use state. So there's lots of different other APIs and concepts in Temporal. So we talked about timers and signals queries. There's also child workflows or external workflows, like a workflow can start another workflow. It can continue as new. And activity APIs, we saw the retries and timeouts, and briefly talked about heart beating. We can also cancel activities. Visibility API, when I built, so the UI that we saw on localhost that had the event history here is built on the visibility API, and I can search by workflow ID or start time between this and this, and other SQL queries against the running workflows or previously executed ones. And where was I? Here was where I was. We have security features. You can all of the input arguments and return values and exceptions that happen are stored in Cassandra in the temporal cluster. If you want those to be stored encrypted, then you can use a data converter to encrypt them using your own keys that the cluster can't see and doesn't have access to. we have testing features like so if you're testing a workflow that sleeps for 30 days, you don't want to actually wait for 30 days, so we can skip time. You need to be able to version your workflow, so you deployed a workflow and they're running, say that they're long running, like a subscription one. You need to be able to update the code to a new version of the code and deploy it without introducing non-determinism into the existing running workflows. You can for debugging, you can save the event history of a workflow and replay it locally, like with the debugger, using a local worker on the same version of the code. In production, we can do logging. We do open telemetry, tracing metrics, and then there's an archival feature for moving old workflows from this live Cassandra to S3. And there's also multi-cluster, which we'll talk about later. So yeah, this is the different parts of Temporal. We have the cluster server, dev tools like the website we saw, and also a CLI tool that similarly can create workflows or get the current status, current history of existing one, or search to find a list of them. And then SDKs we talked about earlier, with more languages coming. That's an old version of the web UI with the task history. Yeah, we sort of already talked about this from going from choreography to orchestration. And some outcomes that we've heard from users are failing to drop data less often, from one production incident a week to 0. When parts of the application do fail, they always recover to a consistent state. So that's a guarantee that the cluster provides, is that any part of it can go down, and it will, once you bring it back up, it will be in a consistent state. People having more productivity, half as many lines of code and infrastructure, and the ability to outsource a lot of the distributed consistent concerns to the platform. Easier to operate. Temporal consolidates errors into this one place where you can view it all, and lets you make fixes without downtime. And as it's an event source system, it's highly observable by default. You don't need to do anything to enable that. So some different categories of use cases. It's a pretty broad thing, but it's often used for business transactions. Coinbase uses it for crypto transactions to do that reliably. The quote from them is, "Temporal maintains a high level of reliability offered by the homegrown system that they originally had and before they migrated, while also providing tremendous amounts of visibility into running processes." Long-running processes like Checker is a background checking service. It's easy to have a human in the loop stage. One of the activities doesn't have to be sort of executed by a function directly. It can just start something async that in an external system that says, okay, operator, you need to hit this button on this this approve button on this web UI, and then once that is clicked, then we asynchronously complete this activity. That's one of the features. And a quote from them is, all new data sources incorporated into our background checks are now done via Temporal, and more specifically by choice of the engineering team working on it. They wanted to because it was so much easier. Data pipelines. So Descript is a tool that allows collaborative audio AV editing. It sort of works like a document, like Google Docs. And so they had one incident every week just to on the transcription workflow because it was too complicated to maintain, and we were afraid of doing any changes in that code path. So I guess if you're designing the system as a single purpose, sort of the duct tape route, it gets to the point where it might be too much for one person to understand, or that when one person leaves, and then it's like a brittle part that you're afraid to touch because it's hard to understand, and you might get it wrong, and then you'll get incidents. So more generally in data pipelines, ML training models, data aggregation and analytics, ETL between different databases. Infra provisioning, so HashiCorp uses Temporal, and a great quote from him was, HashiCorp needs to build long-running, reliable, fault-tolerant tasks for their cloud platform, and Temporal's technology satisfied all of these requirements out of the box and allowed our developers to focus on business logic. Without Temporal's technology, we would have spent a significant amount of time rebuilding Temporal and would have likely done a worse job. So what this reminds me of is, so the Greenspun's 10th rule, if you're unfamiliar, is that any sufficiently complicated C or Fortran program contains an ad hoc, informally specified, bug-ridden, slow implementation of half of Common Lisp. And Temporal's 10th rule is any sufficiently complex distributed system contains an ad hoc, undocumented, unscalable, and unreliable implementation of half of Temporal. So the thing that Hashimoto would have created at HashiCorp to do their thing would have been like half of Temporal, and it wouldn't have, as he said, wouldn't have done as good a job. So when to use Temporal? If you have important work, and reliability is important too, which is pretty broad. It's not just like the use case verticals we just went through. It's pretty broadly applicable. I personally see it as like a higher level of abstraction that you can program at, sort of like you don't have to code in assembly or even C because we have languages that manage memory for you. And so you're working at a higher level of abstraction where you don't have to worry about the dangerous things like stack overflows and tedious things of allocating a certain number of bytes. And in Temporal, we are similarly working at a higher level of abstraction where we don't have to worry about whether the process running my code will die or not, or whether other teams' services are ever down. So I think it's a huge step forward in developing applications in microservices world. There are some cases in which Temporal is not a good fit. If your thing isn't very important, and maybe it's sending notifications and it's fine if they fail occasionally, then it might not make sense to use this sort of system that does a lot in order to provide guarantees that you don't need. Also, if you need something that's very low latency, we're not a good fit because, like, if you're doing gaming and need like a few milliseconds between, like you want to be only limited by the network distance and not take any time processing, basically. We're not a good fit because every step in your code is persisted to Cassandra, and that takes time. We have a great team of like 70 or 80 people at this point. Our two founders have worked for many years at AWS, Microsoft, Google, Uber, largely on this problem of workflow engines. We have a great community. We've got a Slack, a support discourse, a YouTube channel, and we also have lots of companies that use us, that mention us in their job postings, and we have a list on our jobs page of everyone in the community who has postings that use our technology. We also have a cloud offering, so it's MIT licensed, so you're not only free to use it and host it yourself, you can also like sell it yourself. And I guess the proposition for doing our cloud is that it will cost you probably less than your the cost of like the cloud infrastructure, let alone it costs you less to pay us for it than it would for you to host it yourselves, not even including like the cost of the developers to like DevOps people to maintain it. And we can also like provide great guarantees, and we have SLA and support channels and stuff. So if you don't want to maintain a production Cassandra cluster, then use us. Here's some of the diagrams that we got to earlier. And this is sort of all that together. I guess both the sort of services are sharded and also the data store is sharded. And in terms of the CAP theorem, so the CAP theorem says that in a distributed system, you can only have 2 out of 3 of the following things: consistency, availability, and partition tolerance. And basically, we need partition tolerance because we're operating on the internet, and we might not be able to read something over the network, and something might go down. So that one's a given. So basically, it's a trade-off between availability and consistency. And usually, we want our systems to be highly available, so we trade off high consistency for eventual consistency. What temporal is, in sort of in this theorem, like sort of by itself, if you don't consider all the things it talks to, is eventually available and highly consistent. So when like the cluster goes down for whatever reason, whether it's like you configured it wrong and the logs are overflowing the disk, or like the data center loses power or something, it doesn't result in data loss, but increased latency. So like the requests, the workflows will take more time to process because the workers can't reach the cluster at the moment. And if any part of the cluster goes down, the data will still be highly consistent. So it'll recover into a consistent state. And that's like a guarantee we ensure. And if you want more availability, you can have multi-cluster replication. So you can host the other replicated cluster in a different availability zone, different data center, so that if one data center goes down, you can still reach the cluster. Awesome. So there's 10 minutes left. Actually, 20 minutes if we include questions. So I think I will go a little bit more into the code. And we have a question.
This requires some extra care when you implement your services, right? I mean, you have this request ID something. So let's suppose that you send the request, the service processed it, but as you mentioned previously, the response just was not sent out. So your workflow restarts. You get the same request ID again, I guess. And then you need to send back the response again, right? So it's not okay that no change, but you need to send back the response again so the workflow, I don't know, second step can carry on with it.
Yeah, so I think the answer...
Like service B depends on the response of service E, but the response from service E was never received in the workflow. But I don't know, the job was done, like the transaction completed in service E.
So if so if it didn't successfully return the result back to the cluster, then it's going to get retried. And so generally we recommend having idempotent activities. So making sure that you're sending some token to that service so that the second time it gets the request, it knows not to do it, but it's already done it.
Yes, but you need to also return the...
Yeah. So it would say like, I've already done this, and here's the result.
Okay.
And then we could continue. Yeah. So that's like generally recommended way of how to code your activities.
Thanks.
Sure.
You show that there are multiple SDKs for different languages. Does that mean, is it possible to create a polyglot workflow where one activity is in Java, other one is in TypeScript?
Yeah, definitely. The client can be a different language from the workflow, and the workflow can be a different language from the activities. And a single workflow, say in TypeScript, can call activities that are defined in multiple different languages, like one in Go and one in PHP and another in TypeScript. You just have to make sure that the activities you're calling are on the task queue that language's worker is pulling on.
And does the workflow store all the inputs and outputs of every workflow step?
Yep. So we can look at a more complicated case and see all of the inputs and outputs. So that was hello world. Maybe let's look at signals queries. Source. Before that, we have another question.
Yeah, just since we are with the code, after we see the more complex, can we see the overhead of the configuration with providing the worker pool and what does one that uses Temporal actually to do? Because you have all set up, and yeah, it's great. But going back to our station, what do we need to actually maintain in order to use the Temporal functionality? Does it make sense?
I think the question is like, what's like the boilerplate, or what's the
Yes.
setup look like?
Exactly.
Okay. So yeah, back to the hello world example. If we look at the scripts that were involved, no, this is the wrong one. So we were in hello world, package JSON. We were running the start script, which runs the worker, and the workflow script, which runs the client. So this is like the node worker process. So you could deploy this to I guess you could put it in a Docker and have a number of them working in a cluster as your worker cluster, basically just with this start command. And the client script, you could either run it on the command line in your local dev machine as a script, or by operators as a script, or as a serverless function, sort of as we looked at in the first example. And then there's the cluster, which client hosted anywhere. Worker pool started with this, and you scale it up to the number of processes that you need according to your workload, and host it anywhere. And then the open source cluster has a number of services inside of it that uses to run, and then also a data store. And both of those you want to host together, preferably in the same data center as the workers for low latency. And you could either have us host that in the cloud, or you can do it with like a Kubernetes or Astra for Cassandra. And in terms of the code, so that's like the operational boilerplate setup stuff. In terms of the code, boilerplate, the client, we can see that was, we import the client, we set up the connection, and create the client, and then from then on, we're just doing commands like start or query or update, signal, cancel, terminate. But this is all the code setup of the client, and then for the worker, so that was this one. For the worker pool, source worker, what we're doing is we are calling the run and then exiting on any error, and the run function imports this worker class and does .create and then .run. So we're providing the worker the path to our workflow code, our activities functions that we imported, and we're just saying run.
Do you need to customize your workers? So I would imagine that these are just some kind of generic Docker images. So they are workers for your temporal cluster. So they can, I don't know, call and execute requests and stuff, but they are getting their configurations from the cluster. And I don't have to give them anything except just 5 machines that they can run.
I'm not sure I understand the question, sorry.
Okay, so what are these workers actually?
They are...
Do you need to customize it at all? Or can you just run them and they will sync the, I don't know, the workflows that they need to run from the main cluster?
So you're giving them... so it's like you need to deploy this worker code alongside the workflow code and the activity code. So they're all in the same repository here. So the client doesn't need to be in the same repo, but these three files, the workflows, activities, and worker, are in the same
I see.
file and deployed together.
So you are deploying the workflow on the workers instead of the cluster.
Correct, yeah.
Okay.
The cluster doesn't have access to my code. My client, neither my client code nor my worker code.
Okay, thanks.
Did I answer your question earlier? Awesome. Any more questions? Okay, so let's look at a more complex example, both of the code and then also the cluster's view of it, and getting to the question of like where you see the inputs and arguments and return values persisted and saved. Signals and queries. Okay, so we can start a workflow called unblock or cancel. Let's look at what this looks like. We have a signal, which is unblock, so any client can tell me to unblock myself, and then query that just returns a Boolean of whether I'm blocked or not. So we start out, we are blocked, we log that, and then we wait for this condition to happen. So whenever this condition returns true, the function will continue. Right now it's false, so it'll be blocked on this line. And then there's the signal handler just set is blocked to false. So once someone calls this signal, this Boolean will flip to false, this will return true, this condition will resolve, and then we can move to the next line. Alternatively, if we're canceled while we're blocked on this line, we will catch the cancellation error, and we can do stuff here. Right now we're just logging, and then throw it, which results in the end, a terminal failure for the workflow. So we can do that. Now, signals queries, yeah. Okay, so the available scripts are, we can also look at the client side. So we looked at the start workflow, but we can also look at what the query looks like, which is we get the handle of, so we get a handle to a workflow by giving its workflow ID, which we set on start. So this is the workflow ID, and it's used in all of the other scripts. So the script gets that handle and sends the query. And again, what that query will do is result in, where's the workflow? Here it is. Result in this function getting called and returned. So it'll return the value of is blocked to here, and that will get logged by this function. So that's the query. Signal. Similarly, we get the handle based on the workflow ID, and then we signal it, which again results in this function getting called, this handler. And then the last one is cancel. Get handle call.cancel. So first we need the worker running. So npm run start. And let's see, before we start a workflow, what our server state is in. Whoops. OK, so we have the two examples that we did earlier. What we should see when we start something, npm run, what are the options again? Npm run workflow workflow.start. So this will run the script, which should start an unblock or cancel type workflow with this ID. So let's see if that's here. I'll refresh. So we've got the unblock or cancel 0 is the ID, and the type is the unblock or cancel. And oh, we have the worker running. So it scheduled the start of the workflow task, and it completed. And it completed on this line, await condition. So right now, if we do this is block query, it should say true. So we can run workflow.query, and we get back blocked is true. And now we can do the signal script, which will run this handler. Npm run workflow.signal. So it sent the signal and logged unblocked. So if we query now, it should say blocked false. And if we look at the history again, we see that's completed, which we would expect because after unblocked became false, this returned, then went to this line, and then it ended the function. So ending the function is completion. We can see all the other events. So the execution signaled, which is when we called the unblock signal. If we had arguments, it would have been in this array. And we did a couple queries, but those aren't part of the event history. And also, that's why we can't mutate state inside of a query handler, because they're not in history. So we can't like replay it and get you back to the same workflow state. And then when it's completed, the result is empty because we're not returning anything. So I guess this wasn't a good example from the perspective of seeing what data is stored, but it does cover the signals and the queries. And similarly, we can cancel. So we can't cancel this currently because it's finished, but we can start a new one. Oh, I've already started it. Yeah, so I guess there's so I would need to change this workflow ID in order to create a new one. And that's configurable. You can never have two running workflows with the same ID, but you can set it so if you want to only have one currently running. So once it's completed, you can start a new one with the same ID. Let's look at one that has more data. Probably activities examples. Yeah. OK, so we'll have a workflow that calls this make HTTP request activity. And that does a GET request and returns a response. So we should see this return value in history if we run this. CD activities examples. Starting the worker. And we want to npm run workflow. So the sequence for this one, in terms of what's happening, is we run the start script, which starts this workflow, which calls this activity, which is defined here, which makes the HTTP call with Axios library, and then returns this answer, which comes back here, and then we return this from the end of the workflow to the client. So if I run workflow, all that stuff is happening, and then I should get this final return value here. The answer is 42. And let's look at the history to see what happened. Oh, I did start. the cancel gun. Okay. So this is the activities examples workflow we just ran. So we started the activity without any arguments, but when it was completed, we got this result of 42. So that corresponds with what this function returned. And then when we finally finished the workflow execution, it returned this string, which we can see here. Yeah. And I think we only have a couple minutes left, so I will show the last slide, which has, this is a link to the TypeScript SDK documentation. You can subscribe to the mailing list, the YouTube, community Slack. Here's more, all of my social information, including Twitter and email. Feel free to send me questions or come talk to me afterward. Any more questions? Yes. Can we get the microphone too?
So the cluster stores the requests and responses, and you operate the cluster, I mean your company, right?
Or you, it's open source.
Let's say you operate it.
Sure.
Can you make sure that you don't have any access to that data, that only I can read that data? Because
Yeah.
I don't know, it contains like client information that you shouldn't have access to it.
Yeah, so let's go here to look at the docs, and we can see under advanced APIs, data converters, encryption data converter. So you can write this code and provide it to both the worker and the client, and it'll run your custom logic with your own keys. So this is running inside your worker to encrypt all of this data so that you can't see it. That data, this data, any input arguments also.
I see. Thanks.
Awesome. Thanks so much.